Hello and welcome to the MixOps demonstration series, where you can see live demonstrations for real users and real-world applications. For more information about our products or to schedule your own live demonstration, just give us a call or visit us at www.mixop.com. Without further delay, we invite you to sit back and enjoy the demonstration.
So what I have here is a pendant design, or it could be like a coin design, and we'll go through the process of programming these. Now the part what I have here, even though it's a solid surface geometry or it could be a mesh geometry, it's prismatic, as you can see, where there aren't any drafts or sculpted floor surfaces. So parts like these could be programmed using 2-axis, or also known as 2.5-axis methods, or you could be using a combination of 2 and 3-axis methods as well. In this particular part, I'm going to be going over some of the 2.5-axis methods to program this pendant, or it could be a coin design that you could be working on to program toolpaths using our CAM product. Now this can be programmed using our CAM for Rhino, which is RhinoCAM, which I'll be focusing on during today's webinar. You could also be doing this in your plugin for SolidWorks, which is our Visual CAM for SolidWorks, or our flagship standalone product, which is Visual CAD CAM. So the workflow and the methods that we're going to be using would be similar in all our CAM systems. So the first step in here is I would like to go ahead and define the machining process. So I'm going to go to the machine tool setup and determine the number of axes to be 3-axis in here. I'm going to select OK to accept it. Folks, if you are having any trouble viewing my screen, just drop us a note so we'll make sure that you're able to see it. In the next step, we want to make sure we select the post processor. As you all know that our CAM modules include posts for over 225 plus different machines and controllers, which covers a wide range of machine tools that are out there. So you would want to select the post processor that would be most appropriate for your machine. For this particular part, I'm just going to pick a FANUC post processor and select the FOSTED file extension as NC and pick OK to accept it. So you'll now notice that the machine and the post information is set up. In the next step, I'm going to define my stock material. I'm going to go over to stock, and for this particular part, I'm going to choose a box stock in here. And you'll notice that the stock extents are automatically established based on the part. And I'm going to change the length and the width to 60 millimeters. And I'll specify the height to be at 3 millimeters. So I've established my stock. I'm going to display the stock so the stock is being displayed on top of the part. In the next step, I would align it. So use align stock. I would like to face the material to bring it down to the thickness of the part on the top. So I'm going to have the Z alignment of the stock set to the bottom. So it means the bottom of the stock is flushed with the bottom of the part. And then I'll have it centered around X and Y. I'm going to pick OK to accept it. In the next step, I would like to establish my origin. Now there's a couple of ways you could do it. You could use align and set world coordinate system. That could be one of the ways. Or you could use a work 0 and establish your XYZ origin by selecting set to stock box. For the 0 face, I'm going to place it to the highest Z, and the 0 position, I'm going to pick the southwest corner. Now if you're using work offsets or work coordinate offsets or fixture offsets, you can assign the work coordinate offset number by selecting output work offset and assign G54, 55, or whatever your work offset number is. So I'm going to select G54 and then pick generate to establish that. Now we are now ready to program our machining operations. In the first step, I would like to face it down to the thickness of the part. So I'm going to use a method under 2-axis. I'll pick facing. You can see that there are several other methods in 2-axis. You have roughing, facing, pocketing, profiling, V-carve roughing, engraving, slot machining, chamfering, hole pocketing, hole profiling, thread milling, T-slot machining, and remachining. Now most of these methods are offered right from our standard configuration. The remachining is offered in Pro and Premium configurations. So we'll start with a facing operation, and I'm going to go ahead and use select curve edge regions, and I can pick the face edge, or I can pick a curve from the edge of the part, accept my selections. Now for the tool, I'm going to pick a 1/8 inch end mill, which is basically 3.175 millimeters. You notice that the tools I've defined here are loaded from a library are in millimeter units, since the part is in millimeter units. So you need to have a library of tools for inch units and a millimeter units, and these libraries will be loaded based on the library you select to load. The first time you load a library, our CAM module will automatically load the last loaded tool library automatically for you. So it saves you time from having to go back and locate the tool library to load it again. For the feeds and speeds, you can use load from tool, or you can establish your feeds and speeds by selecting load from file. For the clearance, I'm going to leave it as automatic. And when this tab is active, you'll notice that the clearance plane appears on top of the part. In the next step, I'm going to go over to the roughing tab, establish the tolerances, stock to leave, set the cut direction. I'm going to put in my step over distance. I'll put in 40%. Cut levels, I'm going to set it at bottom, meaning I don't want my cut to go below this face. So the geometry I selected, even though it's at the top of the part, I want my cut path to end and not go below this face. So I'm going to pick at bottom, leave the depth as 0, specify any entry and exit parameters if necessary, and then select generate. So I now have a facing toolpath programmed on this part. Now let me go to the Simulate tab and run a verification in here by selecting play. So this basically brings the stock down to the thickness of the part. And since I would be profiling it at the very end, I'm not going in and facing out the material past the part extents in here. I'm going to pick pause and simulate to end to run through the simulation. So we now have the stock blank face down to the thickness of the part. In the next step, I would like to go ahead and clear material in these areas. So I'm going to use an operation called pocketing. So I'm going to go into 2-axis and we'll select pocketing. And in this particular step, I would like to select all of these features for pocketing. I'm going to use select curve edge regions, and I can select all of the curves. I can either type in the select curve command in Rhino, or I can just individually select the curves, or use select by layer, so you can use different techniques to select these geometries. So I've selected all the curves and excluded the outermost boundary in here. Right click or press enter to accept my selections, and now I'll make a selection for the tool. So in this particular step, I'm going to go down to a 1 millimeter end mill. Establish feeds and speeds and clearance, very similar to how we established it on the previous operation. The next step, we'll specify our cutting parameters. We'll set the tolerance, stock allowance. We'll pick the cut pattern in here, so I've set it to offset. The cut direction is set to mixed. I have the step over set, and I'm also going to select the cleanup pass in here as well. On the cut levels, I could pick the depth in here. I can use the total depth control. I can do the pick, and I can snap to 2 points in the model. I can pick the top edge and then the bottom edge of the floor of the part. And there's the total depth, and I can now split this up into multiple depths per cut. Alternatively, I can also use the feature called Use 3D Model to detect depth and just specify a depth per cut parameter in here. I could then establish the entry and exit parameters, specify engage, approach, engage, retract, and departure motions, and also specify any additional parameters in the advanced cut and sorting, and then select generate. So in this process, we are generating a pocketing operation to clear the material out in these areas. So the pocketing toolpath is being computed, and there's the result of your pocketing toolpath with a 1 millimeter end mill. So I'm going to go over to the Simulate tab to run a verification. Folks, if you do have any questions, feel free to post those questions in the questions panel, and we'll try to get those questions answered to you. So at any point of time during the simulation, you can always select pause and then choose simulate to end to run through the simulation, and you'll notice that the progress of the simulation under the progress bar as well. So we now have programmed a pocketing operation which has cleared material in most of these areas. Now there are some areas where the larger cutter was unable to get in. I could go back and program a profiling operation, and this can be done under 2-axis and profiling. So under the machining regions, you'll notice the regions were automatically pre-selected. Since I had the previous operation pocketing highlighted, it automatically added those part regions in here into the part regions under Control Geometry tab. In the next step, we'll make a selection for the tool, and I'm going to go over and select a taper tool in here. I'll pick the 0.3 millimeter taper tool, which has a 5-degree taper angle on it. So for a lot of jewelry applications, you could be working with very small end mills, ball end mills, or even taper tools like these. So if you have a taper ball mill, you would define it under tool type as taper mill, where you can specify a corner radius and the taper angle. Now if the tool also has a flat diameter in addition to a corner radius, you could specify in the flat diameter in here. Now if the tool that you're defining only has a flat diameter without a corner radius, then you would define this as a chamfer mill over right in here, where you can specify a flat diameter and a taper angle. Now if the tool converges to a tip, you would define it as a V-mill, or like an engraving cutter, where you specify a taper angle and the diameter of the tool. So in this particular application, I'm going to be using a taper ball mill, where I have the taper angle at 5 degrees and a 0.3 millimeter corner radius. So these are commonly used tool types in here. So I'm going to pick this tool for the profile operation, and then I'm going to go over to the cutting parameters, where I could set the tolerances, stock allowance. I'm going to choose my cut direction to climb. And since I would like to profile inside on the boundary over here and also outside over here, rather than programming as multiple operations to establish which side to place the cutter, I'm going to take advantage of this feature called Determine Using 3D Model. When I select this, the profiling operation will determine which side to place the cutter based on the solid surface or mesh geometry that you have on the edge of the parts. I have Determine Using 3D Model selected. Now for the cut levels, I'm going to basically pick the depth in here. I could pick 2 points and break it up into multiple levels if needed. Specify entry and exit, advanced cut parameters like arc fitting or corner rounding, and in this particular step I'm also going to sort them based on minimum distance, and then select generate. So in this process, we are now have a profile toolpath generated to go around and clean up around the pendant or the coin design that we have right in here. And now I'm going to hit play to run a verification.
Today, I just like to just point out, if you change the colors of the simulation for each of the operations, that's some of the newer functionality that some of our users might not be familiar with, and also it might look better as far as what we're cutting. That'll be nice. Thank you.
Thank you, Joe. We'll definitely do that. So for the profiling operation in here, I'm going to go right-click on the machining operation, go down to Properties, and I'll apply a simulation color. I can pick a different color from what we had for the pocket operation in here. And now I'm going to select the profile and go back and hit play. And you'll now notice that the profiling operation is assigned a different color during the simulation. So as there's material being removed in the profile operations, you will notice that the color of the cut material simulation is set based on the machining operation that we chose here. So you could set the color based on a tool or based on the machining operation, or leave it at the default setting. So at this point I'm going to select pause and then pick simulate to end to run through the simulation. So you'll notice that these areas that were cleared up where the pocketing operation was unable to get into. So we now have all of the interior features programmed in here. The final step on this particular part is going to go ahead and cut the profile around it. So I'm going to go over to profiling. So rather than creating a new operation by going up to the menu here, I'm just going to make a copy of this operation, right-click copy, right-click and paste. I'm going to now edit this operation and drop all of the regions and just pick the outermost boundary. And to program the outer profile, I'm going to swap this over to an end mill. In the cutting parameters, I'm going to use determine using 3D model to determine the size. And in the cut levels, I'm going to specify the depth in here. So I'm going to pick the depth. I can pick a point near the top edge, and also I can go pick a point near the bottom edge of the part. And specify to go in multiple steps. We'll just break it down to 2 steps. And under advanced cut parameters, I'm going to pick bridges and tabs. I'll do rectangular bridges. We'll give it a bridge height. I'm going to put in 1 millimeter. We'll add 4 bridges in here, and then select generate. So the toolpath shows there's 4 bridges being added in the toolpath, as you notice it right here. So we'll now go ahead and run a verification. So again, I can set the simulation color based on the machining operation or based on a tool. I'm going to change the simulation color over here. I'll pick a different color. And I've set it to apply based on the MOP, which is machining operation, or you could set it based on the tool or default, or leave it to texture. So in this particular case, I'm going to use MOP or machining operation, and then select play to run the verification. So you'll now notice that the cut material simulation appears in a different color, and since we used automatic bridging, there's 4 bridges and tabs created on the part. Now we could also do manual bridge points to precisely select where you'd like the bridges to be placed. Now this can be done by creating a machining region under the regions tab, and then you can add bridge points where you can do manual bridge points and selection. You can also edit bridge points and selection. So for more information on how to create these machining regions and also bridge points, you can refer to the help section, or you can also refer to one of the recordings of the past webinars as well. So this would be a typical workflow on how you would program a pendant or a coin design using 2.5 and 3 axis. Now, if the pendant design also has some additional features like tabs are built into it, you could be programming like a 3-axis toolpath around it to basically, program these features in here as well.